All right, so in terms of then so our diazonium salts then are going to be our last sort of reactions that we can use to add the groups that we aren't able to add that are in our chart that you just learned. So again, as we said last time at the end of class, I'm going to take an aniline, react it with HCl and sodium nitrite, and that's going to give me the diazonium salt, which is going to be stable because the triple bonded nitrogen is in conjugation with the ring. So I don't have to worry about it being explosive the way that if it was just an alkyl group. So if I want to make a diazonium salt, there's an automatic 3 steps. I need to put a nitro group on the ring, reduce it to NH2, react it with HCl, sodium nitrite, to give me an N triple bond N plus. So those are the automatic 1, 2, 3 steps to put the diazonium salt on the ring. So those are going to be important steps to remember, but they all will kind of go together. And then if I want to put a CN group on the ring, I'm going to react my diazonium salt with copper cyanide. That's a Sandmeyer reaction. And so that's going to replace the X group, or the X group is going to become CN. So that's the first way. I can make a chloride or bromide out of it, although it's easier just to use Br2, Cl2, and Fe Br2 or Br3 or FeCl3. Okay. And then all these other reactions. So again, if you want to put an OH group on the ring, you're going to react your diazonium with acid, H3O+. If you want to put a fluorine, it's HBF4. If it's iodine, Ki or Ni. And if you want to get rid of the diazonium salt, just put a hydrogen back on there. It's H3PO2. And some of these are kind of strange reagents, so they really only do one thing. All right, so there's another half a dozen 3x5 cards in terms of reactions. So again, anytime you want to put any one of these groups on the ring, we're now up to an automatic 4 steps. Nitro, reduced to NH2, diazonium, and then whatever reagent here to put that group on the ring. And you don't necessarily have to write all of those individual steps out. You could put like 1 HNO3, H2SO4, 2 Fe or SN and heat, and HCl and heat. So you can write those 4 combinations, but that's what it's going to take to put the diazonium salt and react it. Okay. And then we ended with the idea of these diazo dyes. So when I take the diazonium salt, there is a resonance structure where the plus charge is on the end. That's going to make a large E plus that will only add to an activated ring. And so this is an activated ring. Halogens don't count. This has to be either alkyl group, ring, O, or N. And because the sterics here, this position, adding it ortho to the activated group is going to be pretty small. Most of our group is going to be added to the para position. And when we do that, we end up forming what's called a diazo dye. Now, diazo dyes have a color to them. And in lab, we didn't talk about UV visible spectrometry, and I also kind of nixed that out of the chapter on dienes. So I'm going to give you kind of the nuts and bolts description of why do organic materials have a color, that some have color, some are clear, and how can we change the color of an organic compound. So this has relevance in paints and in paints that we use to put on the wall, paints we use for car paints. Making different colors is a huge industry. right? In Cleveland, it employs how many thousands of people at Sherwin-Williams and around the world, and well as there's Pittsburgh Paints and Glass, PPG. There's a whole bunch of industries that are set up to make color materials. First of all, we're not snakes, so we can't see UV light. We can only see visible. That's all our eyes work under. So in order for a molecule to have a color, it must absorb visible light. And once it absorbs visible light, then it transmits the complementary color or the wavelength, the complementary color's wavelength. So I think if it absorbs yellow, it looks blue. So there's the color wheel that you may have used in art class. There's a color wheel when you're coordinating the power combination of tie and shirt. It's supposed to be the tie and shirt are supposed to be complementary colors, although there's many tie color theories. That's just the complementary color theory. So if you have a color wheel, you can dial in the perfect match. I have the wheel. I haven't been using it for a while, obviously. So the complementary color then is the wavelength of light opposite what the molecule absorbs. So there's that little inverse relationship there. What makes a molecule absorb visible light? Conjugation. More conjugation, the higher the wavelength of light that it absorbs. So just a benzene ring doesn't have a color because it absorbs at 254 nanometers. And that's in the ultraviolet. As we put more and more conjugation on the ring, the wavelength goes up. When it reaches about 400, then it starts to absorb purple. Bless you. And so as there's more conjugation, the higher the wave number, or the higher the wavelength, you see the changes in color.
If you were to try and add another diazonium salt, would it add on the para component to the double bonded nitrogen?
It might, although I think that's going to be more difficult. This would still be an activated ring, but it would be more difficult to sort of make a long chain of these groups because of the steric hindrance. Even though it looks like these two rings are in the same plane, they can't be because of the way the hydrogens would be on top of each other. Plus, I've written this as an N double bond, and that way it would really look something like this because the lone pair's on the nitrogen. So it would be sort of a pseudo-trans type conformation. So we usually don't go more than one ring at a time. But depending on the groups that are attached to these two rings, we can change the color and we can change the wavelength. So this is a diazo dye. Dyes dissolve in solution. Pigments do not. So if you're like painting, that's using pigments as opposed to dyes. Car paints are made of pigments as opposed to dyes. Dyes will wash out. Pigments never wash out. I went to one interview at a paint facility down South Carolina, and that was the first thing I got was pigment versus dye 101. And so they were making pigments. So they're like, don't get any of this on you. Thanks for telling me. As I'm in a suit walking across all this muddy place with my good shoes. And I did get the job. So it was interesting, but not particularly helpful. So you've used these. You've used diazo dyes. I know in general chemistry lab you have a whole sheet of different indicators that you can use along with their color, because that's one of the few color pages that Faith has in her book. And so most of those are diazo dyes, like methyl red. Methyl red is red, or methyl orange. Methyl orange is red, and then in its acidic form and its basic form, it's yellow. And so you get a pH change over a particular range of values. So these are examples of methyl red is another example. And then here's how changing the groups on there will change the color. So with no groups, the diazo dyes orange. Then if you put a nitro group and an OH, it'll be yellow, deep yellow, yellow red if you replace the OH with an NH, and then deep red when you replace it with two methyl groups. So it's not just the conjugation that I'm putting on here, it's the alkyl groups as well. So you can kind of fine tune your dye to the particular color that you want. And then of course you can mix dyes to get, if you want a Kool-Aid dye, if you did a TLC on Kool-Aid, some of the more interesting colors have multiple dyes in them. And those are food and dye colors, FDC. So color is a big deal in chemistry, and people are working, thousands, millions of people are working on trying to make new colors. Occasionally we offer a chemistry of colors class, which should be the physics of color, because it's even more complicated than just chemistry. And the person that teaches that, Dr. Singham, ran the color lab down at Sherwin-Williams before she retired. There's only like 4 color labs in the world. So some companies, because they have one additional compound, can make different shades of red than all the other companies. So it is an important idea, but that's where it comes from. You have to have the molecule have lots of conjugation to absorb visible light. Okay. And so that's how these work. Okay. And I talked about Henry William Perkin last time when he made the purple dye, and the whole dye industry came about from coal tar because of that example. But really what people were trying to do was make medicines from coal tar as well. So that led to development of chemical industry, both in England and Germany, and then over here. So diazo dyes, we kind of give them just kind of a light touch, but they really are important. And so you can, there's whole things on how to dye different things, including with metals, and then you can get into pigments and painting and all of that stuff. So there's a whole chemistry behind that, including like being a art restorer. You need to know a little bit about the chemistry, authenticating the painting so that it's, when you find the $1 million one at the garage sale, it's really the $1 million one and not just a knockoff. And so there are those areas of chemistry. And this is organic as opposed to the metals. Okay, so that's the diazonium salts, but it gives us ability to make C triple bond N, the O's, and the nitrogens, and then F and I if we needed those. So last thing before we go into some of the other different ways we can add alkyl groups to benzene rings, is the idea of sulfonation and blocking. Now, blocking is kind of like protection. We talked about the protecting an OH group so it didn't react, and then taking off the protecting group at the end. Similar strategy, but not quite exactly the same. What we need to remember is that when I put an SO3 and H2SO4 to use that to put on an SO3H group onto the benzene ring, I can take that SO3H group off by using steam. So if I take that product and I pass steam over it, then it will take the SO3H group off, and it will basically just put the H back on. So SO3H groups are removable. And so we can use them in kind of a blocking strategies. So for instance, here's the example I'm going to use. You know, you could say I'm in the lab and I want to be environmentally friendly as possible, or I'm in industry where if I'm not quite environmentally friendly, my company's going to go out of business. So somebody says, hey, I want you to turn benzene into orthobromotoluene. And so we might go to the lab and we might say, well, how am I going to do that? And what would you suggest? Take my benzene ring and add what to it? Kevin? Do you want to add the bromine first? We could do that. So I'm going to put the bromine on the ring. I'm going to put the bromine over here in that position, where it is in the product. All right, now what do I want to do? Add the methyl group. How do I add the methyl group? CH3, Cl, and AlCl3 or FeCl3. Now, where's that going to put the methyl group? Into two positions. The methyl group's going to go ortho, and it's going to go para. So if I'm working at this company and I go, oh, okay, here's my method. This is how I'm going to make the orthobromotoluene for the customer. You take it to your boss, and then they fire you. Well, they should probably ask you one question first. What are you going to do with all this? In the lab, what would we do with that? We just put it in the waste bottle, right? But if we're at a company making 50,000 gallons of this stuff, that's going to be 50,000 gallons of waste. There's no waste jar big enough for that. And the company's going to lose money, and so we're probably going to go out of business. So if we're sitting down and thinking about how can I make this compound then in the highest yield possible, maybe it's going to take me an extra step. But I need to make this and not that. So instead I might say, let's add SO3 H2SO4 to my bromobenzene. And so what am I going to add to that benzene ring? An SO3H group. Where? Well, I'm going to invoke sterics for the first time and say that an SO3H group is pretty big, and therefore I'm not going to get much ortho product. Instead, most of my product is going to be added to the para position. So I'm going to get a high yield of this product. And now what should I do? Now that I've blocked the para position, now let's go ahead and react that with methyl chloride and AlCl3 so that the methyl group is forced to add to the ortho position next to the bromine. And you could probably argue and say, well, so how's the methyl group going to add ortho? when the SO3H group, we didn't add ortho. Two different arguments here. SO3H is going to preferably add para versus ortho. In this case, the methyl group's got nowhere to go. It's got to go ortho to the bromine. So I get the methyl group on there, and then what do? I treat this with some steam and then strip off the SO3H group, and so therefore I've made my product in a much higher yield than I did if I just added the alkyl group to the bromobenzene. Josh?
Would you be able to add the methyl group first instead and still come out with the same steric hindrance and
Right. So the other option that we could do here is we could have started with the methyl group and then added the bromine in the second step. And you would have gotten the same exact results. So the idea of this blocking strategy is you can use an SO3H to block a position that you don't want to add something to and then strip it off later. And that can help you. In the case of making ortho disubstituted aromatic compounds, it's the perfect way to do that. Does everybody kind of see that? And if you go back, if you go back and start looking at some of the older exams for next week, you'll see that oftentimes I'll ask questions that make this compound from benzene using a blocking strategy. And that's what I intend here, is that you use the sulfonation as a blocking strategy.
Can you block like one more spot?
You could. You could, and you could also block a meta position if you needed to. The only problem is going to be that these groups are not going to want to go next to each other. So you're either going to want them para to each other, or maybe, and para you can't get, right? Because once the ideal situation here is that these groups are down low on the totem pole here of directors. So when you put it on the ring, you're not going to change the director. Whatever was on there first is going to still be the director. Now, I would have added the methyl group first to the ring instead of bromine, simply because if I'm going to go to the level of detail about thinking about yield, I'm also going to think about the energy that it takes for this reaction if I'm going to make 50,000 gallons of this. Because, a little bit more heat from Bunsen burner is nothing, but a little bit of heat on 50,000 pounds of stuff is a whole other story. And I might put the activating group on the ring first, because then that's going to cause the reaction to occur a little bit faster when you put the bromine on. When I put the bromine on, it's going to be a deactivated ring. I might need a little bit of energy that I wouldn't have needed if I just would have put the methyl group on. But a lot of this stuff would fall into the realm of being a chemical engineer then. So the chemist would sit down, say, this is how I want to do it, and then the chemical engineer would come in at a higher salary and figure out exactly all the necessary details to put that together. So we can, we're 3/4 of the way through the semester here. And so just to give you kind of a glimpse of what we really need to consider, not everything on paper works well. And so we have to begin to think about what are some of the nuances. And this is a nuance. Okay. So not only do you have to know the chart that you hopefully now have in your head, and don't let it escape, but you also need to know, how do we make these particular groups, and then what groups do we make with the reagents. The folder after today's is EAS problems. So there's tons of problems to take a benzene ring and add groups to it. That'll help you hopefully learn your reagents. I would not do all of them, but I would do as many as you see fit. And that's why I'm giving you the problems that are due on Friday. They were on Monday. What's in the folder today is due on Monday, but I don't know if we're going to get all the material that's on that folder today. I haven't gotten a chance to look back at it and see. Okay. So this is the electrophilic aromatic substitution reactions and what we have to think about. But there are more. So what I want to do, and what the next section of the Top Hat book wants to do as well, is to give you a little bit of an idea about what real synthetic people do nowadays. It's not that they don't do the reactions that we learn about, but there are some nuances. It'd be really great if I could run my reactions in water as opposed to organic solvents. That would be more environmentally friendly. Transition metal catalysts are sometimes incredibly important because they allow us to basically get down to an atom efficiency so that I don't have to have an excess reagent. I can pretty much hopefully utilize every atom that's in the reaction. These are all principles of green chemistry, which people are trying to improve basically the sustainability of their reactions. And when you're synthesizing drugs, just a lot of these basic reactions don't work. So let's go back and remember lithium cuprates as sort of an entree to this. So let's say that I wanted to add that alkyl group to my benzene ring. Now, a lot of times what we'd have to do is add the alkyl group, and if there were any other groups on here, I'd have to start doing side chain reactions, which would involve like free radical halogenation, doing elimination, all of that stuff. But if I wanted to make this molecule, I could go back and I could remember a little bit about the lithium cuprate chemistry that we talked about with Grignards. And assuming that everybody needs a refresher on that, then let's go back and kind of review what that would mean. What that would mean is that I would take my alkyl group and I would have a bromine on that, and I would treat that with lithium as opposed to magnesium. But I would get a negative with the lithium positive counter ion. So I'd basically make like a Grignard C-. I would then react that with copper iodide to make the lithium cuprate. My stoichiometry is all messed up here. I'm not going to go back and make everything add up. But in the lithium cuprate, we have two anions, a lithium plus and a copper plus. So I could take any alkyl halide that I wanted, make the organolithium out of it, and then make the lithium cuprate. Now, how am I going to make this this benzene molecule? I'm going to couple that, because if you remember from the lithium cuprates, what we do is we react the lithium cuprate with an alkyl bromide, or in this case an aryl bromide, and that's going to couple the two alkyl groups together. So now that I make my alkyl halide and aryl halide with the benzene ring, I'm going to couple those two together, and so I'm going to end up then coupling that basically sec-butyl group with the benzene so that I can make it in a pretty efficient method. So remembering, hopefully, a little bit more about the lithium cuprate reagent, what we can now do is we can actually sort of broaden our perspective here. When you're a synthetic chemist, you want to come up with methods that will let you add groups, and you want the broadest sense of groups that you can put together. So the lithium cuprate chemistry allows me to say, you know what, I don't care what alkyl group I want to put on the ring. All I need to do is to make that alkyl group and put the bromine in the position that I want to add to the ring. Then you make the organolithium out of it, the lithium cuprate, and couple it to the ring. So that gives us a lot more flexibility, as opposed to putting an alkyl group on the ring and trying to play around with all the side groups. Somebody makes this, and we couple it together. So that's the kind of reactions that people have come up with in order to be able to add sort of any group to a benzene ring. And so this is lithium cuprate coupling. There's several other coupling reagents or reactions. There's Heck coupling, there's Suzuki coupling that we'll kind of get to in terms of this same overall process. The problem with this is still an air and moisture sensitive reaction. I still need organic solvents for this reaction. It would be nice if I could change the metal from lithium to something that I could use in water, and that's something I could use as a catalyst, where I could just basically take that metal catalyst out and reuse it over and over again. And so that's what the next sections of the textbook talk about. So, between now and Friday, well, now for a few minutes, once I find my cheat sheet of paper, organization's out the window again. Well, it's completely out the window now. I'll be taking my life in my hands if I have to improvise. Okay. If you're going to go on and teach, never do that pre-tenure. Wait and do that after you have tenure. Because pre-tenure, it's a bad review if somebody's watching you. Although when I was pre-tenure, I mixed up upfield and downfield and shielding and deshielding for an entire lecture. And then somebody at the end goes, didn't you just get that completely backwards? Yeah, I did. I was trying to show you how difficult it is to keep it all. I'm still here, so I must have overcome that. Okay, so let's put some different things on the ring. Let's go back and talk about something I put a big red circle X through on Monday. Let's say that we wanted to take the benzene ring and we want to make benzaldehyde out of it. I mean, benzaldehyde is actually could be used as a flavoring or a fragrance. And I want to do this in one step. Someone might suggest, as they did on Monday, that, we'll just do this. And actually, this isn't bad, because, we're trying to extend our reagent, and at the time, just like on Monday, you didn't necessarily know that you can't do that. Well, we can't do that with this one. And this is an aldehyde versus on Monday we had a carboxylic acid. So it turns out this set of reagents will not work. Why? Just simply because this is an unstable molecule, this acid chloride of formaldehyde. And so we have to come up with another method of doing this. And the way to do this, industrial, which is done, is to use what's called the Gatterman-Koch formulation. I didn't spell formulation wrong. Like formaldehyde. This is formaldehyde. And we talked about formaldehyde when we did triple bonds, and we said if you cleave a triple bond at the end of the chain, or if you cleave a double bond at the end of the chain, you make formaldehyde, and then that gets oxidized up to CO2 and water. So Gatterman Koch, what they said was, this is an industrial where we take carbon monoxide and HCl along with a catalyst of aluminum trichloride and copper 1 chloride. So what they're doing is they're actually taking the carbon monoxide and adding HCl to it. So if you think about what carbon monoxide looks like, it looks like this. And if I add an HCl to that, what I end up doing is adding the HCl to basically make this formerly unstable reagent, and it's still unstable, but if I make it fresh, hopefully it reacts before it decomposes. So this is what they make from the carbon monoxide and HCl, and of course then the AlCl3 immediately generates the acyl carbocation. So the idea here is that I know I put an X up here in terms of making that, using that, but you are allowed to make it and then have it react right away. And so this is kind of an industrial preparation of benzaldehyde from benzene. And so not all these reactions won people Nobel Prizes, but they're at least associated with their names. So Gatterman and Koch, I think I have Gatterman's organic lab book from the early 1900s upstairs. So this was about the time that he was, late 1800s, early 1900s is when Gatterman was doing this. So then the other kinds of reactions that we're going to do on Friday will be to take and couple. So I showed you as an entree the cuprates. What we're going to want to do is we're going to want to basically make an alkyl group of some sort, and we're going to couple it with the benzene. So there's different types of coupling reactions that we're going to do. And we have Suzuki, we've got Heck coupling, we've got Suzuki coupling, we've got boronic ester coupling, and then there's different methods that you can use to make like phenols beyond the diazonium salts. So this is all in the, I think, last section of chapter 21 in the Top Hat book. So that's what we're going to go over. I have a video of me talking about this, but I think towards the end it gets really bad because of the scribbling. So I'm just going to do it live on Friday. But that's where we'll be pulling it from. And if you look at the problems from today in today's folder, and there are these kinds of problems, we'll do this on Friday so that then you can do them for Monday. Keep those, yes, because those are what we will use when I ask you a multiple choice question.